Do you guys have any questions? Any questions on this homework example? Okay. If you don't have questions on this, give me a thumbs up on the YouTube live stream so I can move on to the new examples for today. You just give me a thumbs up on the YouTube stream, live stream. Okay. All right, good. Just help me to get some reactions from you guys. Otherwise, hard to see everybody's reaction. Okay. Okay, next, we're gonna. That's just for homework, and I think in order to give you a little bit more time to work on the homework, we extended the due date for this concept homework to the same day as the problems homework. So if you haven't got it done, you will have a little bit more time to do it. Now let's look at some more examples in this section. Let's see. Let's look at. Okay. Let's first look at this example 4b2, which is the same example on your book. The second example in section 4b. And in this example, we have a block that's sitting on a rough surface, and this surface has an angle theta. And at the bottom of this surface, there's a spring here. And so this block M is released from rest, and it will sliding down, right? And you will hit this spring, and it will compress the spring. So this problem is asking you to find out what's the maximum deflection of the spring. So in this example, we know the mass of the block, we know the distance at the initial position from the spring, we know the spring constant, we know the mu k, which is a friction coefficient. We also know what's theta of the surface. And yeah, how to find this maximum deflection of the spring. And so I want you to recall this 6 steps approach we learned on Wednesday. So I'm going to call some of you to tell me what are the steps. And you can unmute yourself to answer the question. How about William? Tell me what's step 1 to 3. Just unmute yourself and talk. No? Okay, how about Chickup Rider? Can you tell me what are the steps? Just make sure you guys, my microphone is on. Yep. No? Can you unmute yourself? No? I couldn't hear anything from. Let's try this. Yep. Okay. Yeah, first step, draw free body diagram. That's good. Okay, I don't think this worked very well. Alright, I will just start this problem. Okay, solution. Oops. So step 1 to step 3. So step 2 should be free body diagram and coordinate system, right? It's the same step as the yep. Okay, I hear someone's trying to ask questions. Okay, so step 1, 2 should be pretty easy. I want you to do this on your note as well. So draw the free body diagram. So first take that block and draw all the forces on that block. The block should have a weight force going down, and you need to have a normal force to support this block. And friction force, F, and also we're gonna have a spring force once it hits the bottom, right? So we should add that spring force down there as well. So those are all the forces we should have on the free body diagram. And what coordinate system you would choose for this problem? And if you look at this problem, xij should be enough. So I will set up my ij line up with this slope. This is ij. Okay, now once we have those step 1, step 3, and last time we mentioned step 3, what should you do on step 3? You should apply the work energy equation, find all the kinetic energy for each mass. So the kinetic energy in each mass. Here we only have one mass, right? This is the only block has mass in this problem. So we just need to talk about the kinetic energy of this mass at position 1, which is at the time when it's released, and that is 0, since we don't have any speed at that time. It released from rest, so that's why T1 equals 0. And T2 at position 2, so when it sliding down, compress the spring to the maximum deflection, and at that time this block is stopped, right? Before it bounces back, at that moment it has no speed, therefore T2 equals 0 as well. And now let's move on to step 4. At step 4, and we need to figure out what are the works or potential from each force. So you need to analyze potential energy. Let's call it PE. Potential energy for each force in free body diagram. And in step 3, I would just write down here that would be kinetic energy KE for each mass. Okay, so I want you to pay attention to the wording here. For kinetic energy is for each mass, and for potential energy is for each force. Okay, now let's go back to step 4. We need to find potential energy or work. For each force. And how many forces we have in our free body diagram. 1, 2, 3, 4. 4 different forces. Okay. Let's start with the work done by normal force. And can you tell me what is the work done by normal force in this problem? You can just type the numbers on the chat. Do anybody know? Yes, it would be 0. That's correct. There's no work being done by the normal force. Why is that? Some of you may have questioned why there's no work being done by the normal force. So if we look at this, normal force is pointing to the j direction, but I want to ask you, is there any, there's no movement, yet perpendicular to the movement, therefore no work being done by the normal force. So that's red 0 there. And let's move on to the next force, weight force. And I think we do have something from the weight. Okay, I shouldn't write that way. For weight force, and that we can express that as capital V, which is potential energy from weight force at position 1 should equal to, if we can set up, this is our Dayton 0 potential line. So at that time, potential energy from the weight force equals 0. We can do that as 0. Then, because weight force is a conservative force, so you can its potential energy depends on both endpoints, right? So at position 2, your weight force work, that potential energy equals what? When the blocks move downwards to hit the spring, so H should has a displacement in a certain height. Let's just give let's just use H. This should be mgh. Okay, these two expressions here, V1, V2 from weight force represents the potential from weight force, and also you can call it the work done by the weight force. And let's move on to the other forces on our free body diagram. Here we have FF. That's the friction force. Friction force, it's a non-conservative force, so we cannot write that as a potential V1, V2. You have to write that as a work. So write as U, FF, that equals to, and if you remember the notes last time, it has the integration with S1, S2, and FF dot product et hat ds. And because in this case the F, the friction force, is constant, and the direction of movement motion is constant, is at the same direction, so you can simplify this whole thing as FF times S, which is the path, the length this block traveled on the slope. Okay, so that's the work done by the friction, the non-conservative force. And let's look at, we have one more force, which is this spring force here. The spring force is a conservative force, so we can write the work done by spring force as potential energy V1, V2. So let's write V1. Once S represents spring, potential energy at position 1, which is right there, and the spring is unstretched, so there's no potential energy. Was it 0? But at position 2, and the block is compressed the spring, therefore there is a potential energy from the spring. The equation is 1/2 times k times delta x squared. That's a potential energy from the spring, and it is always positive. So remember, keep that in mind. The potential energy from spring is always positive. Okay, these two forces, these two potential energy come from spring. This two is from weight force. So far we have analyzed all the potential energy or work done by the non-conservative force at step 4. And then you will realize that we don't really know what is this friction force, FF here. And yes, we don't know the exact value of FF, so you would need to use the method we learned in section 4a. Remember, in section 4a we also have 6-step approach to solve some unknowns. You need to use that to solve what is FF. So I think that would be a good review. Also kind of to show, let me write that down on the other side. So okay, I will just draw a straight line here. In order to find this FF, we need to use the approach from 4a, which also has 6 steps, right? The first 2 steps are the same with what we have here, but start from step 3, it's a little bit different. And start from step 3, I want you to remind yourself what is the... Oh, I just saw someone ask a question, would the potential for the weight force be negative? That's a good call. I missed the negative sign here. So mgh here, because h is below the reference point, so that should be negative. Thank you. Okay, now here we need to use, let's go back to, by using the approach from 4a to solve for FF. So the steps 3 we learned in 4a is to find all the forces in your free body diagram and write them in a vector form, right? And then we can write that down to N equals Nj, weight force equals mg negative mg cosine theta j plus g sine theta I. That's I. And you have 2 more forces, FF equals negative Fs I direction. Oh, that's F. We also have a spring force, F spring equals negative Fs what direction? I direction. And then step 4 is to write all the accelerations. Force acceleration of this block, right? A equals A, which is only I direction. Oops, that's I hat. And step 5 for A is to apply F equals ma and extract the scalar equations. In this case, I will skip that, just jump to the J, because we only need to find out what is the normal force in order to find what is the friction force. So if you extract scalar equation from j direction, you have n minus mg cosine theta equals 0, and you will find out n equals mg cosine theta, and therefore ff can be found by use mu k times n, which is mg cosine theta. So as I said, the problems are getting more complex because you have to use the method we learned previously to solve something in order to keep working on the work energy equation. But now we find out this friction force, we can move along with the work energy equation. And do you still remember the work energy equation? Can you write it down? What is work energy equation? So it has T2 plus V2 equals T1 plus V1 plus this important term here, which is the work done by the non-conservative force from 1 to 2. So this is a work energy equation, and you just need to plug in all the terms we find previously into this work energy equation, and you're able to solve on those. So this is step 5. Oops, let's change colors here. So I just want you to clarify here, the red color here on the left side, it's the work energy method in 4b. So we have step 1, 2, 3, where's 4? 4 and 5. And on the left side, it's something we learned in section 4a. We need in this part to solve what is FF, which is force, friction force. So just make sure you're clear with all of those. Let's keep. If you substitute everything into the work energy equation, and you should able to have a long equation that is k over 2 delta x squared minus mgh2, which equals negative mu k mg sine theta. That's cosine theta. Cosine theta times the distance, the path s. Okay, I think Zoom, you can just keep that solved. You can re-log in if you want to. Okay, and you were able to solve what is this delta x there, and this delta x, h, and the s has some relationships, right? Because how that block is traveled, and the block is traveling downwards to compress the spring, and that distance is traveled, the total distance traveled is equals to delta x plus d, and the height h there can be solved by using the angle theta. So h there equals, here we need sine theta equals h over delta x plus d. Then in this way you are able to solve what is h. Right here, h equals sine theta times delta x plus d. And you can plug this h into the work energy equation, and to solve and plug this s equals this into the work energy equation to solve what is delta x. So eventually your delta x is in a quadratic equation as 500 delta x squared minus 30.4 delta x minus 22.8 equals 0. So you can solve this. You probably know this is power to the second. You will end up with two values for delta x, and you will need to take the positive result, right? It's because the compression of the spring cannot be negative. So if you solve everything, you should find delta x equals to 0.184 meter. So that's this problem is a little bit long, and you kind of have to combine the method from the previous section in order to find friction force, then use friction force to find out what's the work done by the friction. So hopefully this shows you how to set up everything. Okay, then now I will go back to Zoom and to ask questions. So let's look at this example 4b1. In this case, we have a rigid bar, and on one end of this bar, there's a particle P. So the whole bar, the rod, or whatever you call it, has no mass, so 0 mass, but this particle P has a mass of 6 kilogram, and is attached there. And at the other end of this rod, there's a force no more to the rod is pushing this rod. Sorry, the total length of the rod is 2 meters, and if this rod is released from rest when theta equals 0 degrees, which is straight up, and the force equals 100 newtons normal to the rod. We need to find out what is the velocity when theta equals 90 degrees. And so let's go through the steps. Step 1 to 2, free body diagrams for the rod. And have 3 forces: weight force, and the normal force to the rod, and also we have a reaction force here, a resultant force at the middle. That force has a changing direction, depends on the angle of the rod. And then step 3, we need to find all the kinetic energies for each mass. And in this case, we only have one mass, which is that particle P, and the kinetic energy is T1, T2. It's 1 over 2 mp Vp 2 square. And at position 1, that is 1 over 2 mp Vp 1 square. And because it starts from rest, so Vp 1 square equals 0. And that's step 3. And step 4, you need to find all the work or potential energy from each force on your free body diagram. So the weight force can be written as potential at position 1 and 2. So at the beginning, you have potential mpg times 0.6 L, and that's position 1. Let me double check that. Okay, and like the question Kira asked, and you need to set up your kind of reference, zero potential reference for your gravitational work. So here in this case, I think this is a reference point setting up below that joint. That's why at the beginning, the particle P would have a potential energy of 0.6 L times mpg. And at position 2, because that rod will rotate to theta equals 90 degrees, so it goes to the particle will be at that 0 potential position. That's why V2 equals 0. Then if you look at our free body diagrams, we just analyze the potential from W. We still have 2 other forces, and those 2 forces are not conservative force. So the work done by them has to be written as an integration form. So the first force is a reaction force R, and the work done by the reaction force R can be written as this. But if you look at where's the point of that force is pointing to, that pin joint is not really moving to anywhere. That's why the work done by the reaction force here equals 0, because there's still movement. And we look at this normal force F applied to the rod, and this force is applied to the rod, and it does move from one position to another. So you need to consider the path that force is applied to the rod. The path that force applied to the rod equals R, which is the radius of the rod from F to the center, times pi over 2, which is 90 degrees, how theta changed. So it's pretty much, this is F times S. S is a path. In this case, that path is a curve. At the starting point, this is a rod, the center of the rod, this is the force, and the path looks like this. So this is a path S. And the work done by this force can be calculated by use of force times the path. And step 5, substitute everything into the work energy equation, which is your T's and V's, which is our potential energy, as well as this non-conservative work done by all the forces. And then once you plug in everything, that should give you a long equation, scalar equation, that you can solve up to at least one unknowns. In this case, Vp2, the speed of particle at position 2, is the only unknown. So we're able to solve that. Vp2 equals square root 1.2 GL plus Fr pi over 2. So that's a kind of a quick rundown on this problem. And as you can see, we stopped at step 5 because we already solved everything. However, in some other problems, you may need step 6 and to get one more equation to solve up to more than one unknowns. And in that case, you will need knowledge from chapter 1 to chapter 3 to create that one more equation. And so I think this is a good time to kind of bring up one of the problems homework that is due next week. So if you have started with the problem homework, I will pull that out. In the first problem of your problems homework, and you have this kind of two blocks, A and B, and A can only move on this horizontal surface, but B can slide up and down on this guide. So in this case, you can still follow the step 1 to 5 to build your equation, but you will run into a problem that after step 5, sorry. Once you finish step 5, you will realize you have two unknowns. One unknown is VA, and another unknown is VB. That's VA2, VB2. So that's the speed of both blocks at position 2, which is drawn in red. And we realize you only have one equation but two unknowns, and in that case you will need a step 6 to build one more equation to help you solve VA or VB. So this equation will be an equation to show the relationship between VA and VB. So by looking at this problem, the rod in between A and B, it's rigid, so it won't change the size and shape. And another thing is this block A can only move on this I direction, block B can only move on J direction. And this is something very similar with what we learned in rigid body kinematics. So it's also very similar to the pulley rope problem we learned. So in this case, we can write the change of position of A, block A, can be only on I direction, right? And the change of position of B can only be on J direction. SA, SB, and how much they can change, it's constrained by that rigid body, that bar over there. So actually you can use a triangle now to show distance is L, which is the length of the bar, and this is kind of our SA, this is kind of our SB. So the relationship between those three should follow the right triangle law, which is L squared equals SA squared plus SB squared. Yep, so you have to use something, find a relationship between them in order to solve this problem. And remember in the homework, in chapter, I think that's 2, you can take a dot on both sides of the equation, right? In that case, you have L, dot, double dot, or dot, depends. In this case, we only need first order derivative. Then you will end up with something, I will leave that for you, something with VA and something with VB. In that case, since the length won't change, so this whole term goes to 0, you would able to build a relationship between VA and VB to solve this problem. Alright, so I will leave the rest of the problem for you. And if you have any questions, feel free to just like unmute yourself and talk through the Zoom. I will stop our Zoom meeting. Hope you guys have a good weekend.